Hello everyone. In this class, we are going to discuss propagation of radio frequency electromagnetic waves in free space. So, the basic elements of communication system are transmitter, receiver and channel. So, in order to send the information from the transmitter to the receiver, the channel, it may be a cable or it may be free space. So, for example, communication using radio waves. So, at the end of transmitter, the antenna radiates electromagnetic waves and they travel in space and reaches the receiver. So, here these electromagnetic waves, when they travel in space, their strength goes on decreasing. Because of the damping, some of the molecules of the medium will absorb the energy. Because of that, the strength of the electromagnetic waves decreases. There are several other factors which also influence the propagation of these electromagnetic waves. So, it is important to know the composition of Earth atmosphere as it plays an important role in the propagation of these radio waves. So, we must know about the Earth's atmosphere. So, the reason for it is the atmosphere will affect the propagation of EM waves. Right. So, here we will see the role of atmosphere on the propagation of radio waves. EM waves, in this case it is radio waves. So the Earth atmosphere allows EM waves in the visible range. That is why we have light coming far from sun onto the Earth surface. And atmosphere's ozone layer will block the UV radiations coming from the sun. And EM waves of a few kilohertz to 3 megahertz, they glides near the Earth's surface. These are called ground waves. And EM waves whose frequency in the range of 40 megahertz, they are reflected by different layers of ionosphere. So these are called sky waves. That is, here what we have to see is the atmosphere will influence the radio waves, and electromagnetic waves whose frequency is more than 40 megahertz, they penetrate through the ionosphere and they always travel in a straight line path. So using these electromagnetic waves, we have satellite communication. So different layers of the Earth atmosphere will have different effect on the propagation of electromagnetic waves. So here there are three different type of radio frequency electromagnetic wave propagations. So first one is ground wave propagation, second is sky wave propagation, and the third one is space wave propagation. So we are going to discuss in a detailed way about these three types of wave propagations in free space. So what is meant by antenna? We have an antenna at the transmitter and also at the receiver end. So antenna which converts the electrical signal into EM wave to radiate into the space. We know that electromagnetic waves can travel in vacuum or in space. So for that reason, this electrical signal must be converted into electromagnetic waves. So as I said in the earlier slide, the atmosphere will affect the propagation of electromagnetic waves, and the Earth composition and its density is changing continuously from place to place, and as we are going from away from the Earth's surface, means if you change different altitudes, the density, composition is changing from place to place and is also changing with seasonal conditions like summer, winter, depending on the conditions of season, and also at different altitudes, the composition of earth and density, they are different. So here we can observe some animated pictures showing ground wave propagation, sky wave propagation, and space wave propagation. So see here, the receiver can receive the ball in 3 different ways. So the other person is a receiver, so he can receive the signal nothing but ball in 3 different ways. So the first one is rolling on the ground. So this kid is rolling the ball and the receiver is catching it. So the other method is by throwing the ball directly. So if both are in the same line of sight, so the transmitter, this boy is sending the ball and the receiver is catching. So this is if both of them are in the same line of sight, so throwing directly to the receiver. So this is called, this type of catching a ball, we call it as space wave propagation. And third one is sky wave propagation, in which this transmitter, nothing but this girl is sending a ball, she is throwing onto the roof, and from the roof the ball bounces and then it reaches, here the ball is bouncing, for example assume here the ball is touching the roof, from that the ball is reflected and then it reaches to the receiver. So there are 3 different ways in which a ball can reaches to the receiver. First one is rolling on the ground, or throwing the ball directly, or throwing the ball onto the roof and then it is reflected to the receiver. So this is sky wave propagation. So and with animation, just I want to convey different wave propagations. So now we will see ground wave propagation. So here these ground waves follow the curvature of earth. So here you can observe from the transmitter antenna, these ground waves, they are following the curvature of the earth surface. We will see why they follow the earth surface. So here the frequency range of these ground waves is very less, in the range of kilohertz to megahertz. So to radiate the signal from the transmitter with high efficiency, if I want to radiate the signal with high efficiency, the size of the antenna must be comparable to that of the wavelength. So the size of the antenna is approximately lambda by 4. So these ground waves, as we already said, frequency is less, means wavelength is large. So for longer wavelengths, lambda is large, so the height of the antenna is very large. For these ground waves, the size of the antenna is very large. And here these antennas are located on the earth surface or near to the earth surface. Maybe we have vertical towers on which we can have antennas. But whatever may be, as we said, the size of the antenna is large depending on the frequency. So depending on the frequency range, the antenna size is given by lambda by 4. But whatever may be the antenna size, these antennas are close to the earth surface. They are close to the earth surface. So here these waves, ground waves, are also called surface waves. These are also called surface waves, and these surface waves are influenced by the ground. That we are going to see in what way they are influenced by the ground. Suppose if you are sending a ground wave, electromagnetic wave. So here we have electromagnetic wave. This is positive amplitude and this is negative amplitude. So here these is nothing but the electric field vector. Here what we are observing, because electromagnetic means we have both electric and magnetic vectors. So here we are showing only the electric field vector. So here the electric field vector is perpendicular to the ground surface. So if the electric field is perpendicular to the ground, these are called vertical antennas. These are called vertical antennas. So whenever these ground waves are propagated, these ground waves are also called surface waves. So these ground waves induce current in the earth. So see here, if there is a negative charge, by the induction on the earth there is a positive charge. So likewise the charges are induced in the earth. So and from on the earth surface, maybe there are some mountains, or there may be rough surfaces. So at those places, these electromagnetic waves get short circuited. Means that this electromagnetic wave meets the earth, so there is a short circuiting because of the different as it is moving very close to the earth surface, and because of the induced charges on the earth, there is a chance of short circuiting. If short circuiting happens, so the earth absorbs this electromagnetic wave energy. So because of the induced current, short circuiting occurs, and because of the short circuiting, the energy of the electromagnetic wave is absorbed by the ground. So there is a attenuation, means the strength of the electromagnetic wave decreases. So that is called attenuation. So attenuation is because of the short circuiting. And as I said, in order to minimize this short circuiting, we use vertical antennas in which the electromagnetic wave is, or the electric field vector is perpendicular to the earth surface. So because of the induced charges, the electromagnetic wave gets absorbed by the earth, right? And so we use for electromagnetic, for AM broadcasting, we use vertical antennas instead of horizontal. Horizontal antenna means that the electric field is parallel to the earth surface. So here we can see, so this is a vertical antenna and this is a horizontal antenna, right? So as we said, range means the distance, maximum distance between the transmitter and receiver. So because of the short circuiting, the range of these ground waves is less, and the range, we can able to increase the range by changing the power of the transmitter. We can able to change the and frequency. If you change the frequency, as the frequency is high, we can able to increase the range. But for these ground waves, due to short circuiting, the range is limited. And for these ground waves, because of the induced currents on the earth surface, the attenuation means decreasing strength. So with the increasing frequency, as we increase the frequency, the attenuation also increases. So there is no use of increasing the frequency. And here these are low frequency, means high wavelength. So according to diffraction, first order maxima, A sin theta is equals to 1 lambda. So lambda is large, it means theta is also large, means bending effect is more. For example, from this transmitter antenna, if ground waves are propagating, so they are bending more towards the earth. So this bending is because of this large wavelength, and the theta is also more. So in that way, these ground waves follow the earth surface because of the more bending effect of the ground waves. So for example, so the applications of these ground waves are Wi-Fi, walkie-talkie, and some of the AM radio stations based on these ground waves. So for example, if you have Wi-Fi in one particular room, and we will get this Wi-Fi signal within the house. The reason for it is because of the ground waves whose wavelength is large and bending effect is large. So whatever may be the obstacles present in the house, these ground waves will bend at the edges of the obstacles, and we can able to get access of these Wi-Fi signals. So this is about the ground waves. Sky waves or sky wave propagation. So these sky waves have frequency 30 megahertz to 40 megahertz. So the frequency is somehow more than the ground waves. So for long range communication, we can use these sky waves. We can use this sky waves. So here in this sky wave propagation, the waves reaches the receiver after reflection from the different layers of ionosphere. We have different layers in the ionosphere. So here observe from this transmitter, the sky wave is propagated into the atmosphere. So at one particular layer of the ionosphere, the sky waves gets reflected. So this ionosphere layer acts like a reflector, and it reflected from that layer and it reaches to the receiver of the receiver, which is kept on the Earth's surface. So what is ionosphere? The name itself indicates it contains large number of ions. First of all, why we have ions? Here as we have number of molecules, at the atmosphere contains different molecules, and these air molecules will absorb the sun energy and they get ionized. So at different layers of atmosphere we have ions because of the absorption of sunlight. And we know that why we have a reflection at one particular layer, that we are going to understand. So here when for one particular height, let us say far from the earth or far from the earth surface, it means that the intensity of the sunlight is large. Intensity means the number of photons are very large, and as we move away from the earth, the density goes on decreases. Density goes on decreasing means the number of molecules available decreases. So first of all, let us consider at a height far from the earth. So where the intensity of the light is high and the number of air molecules low, as we are moving away from the earth, density decreases. So because of this, the ionization of the molecules is less number. We have only 10 atoms. So the ionization takes place, only we have 10 ions. Now let us say, for example, now we come to close to earth at a height very close to earth, where the sunlight, after traveling over different layers, the sunlight intensity decreases. So the intensity of sunlight is small. So very close to earth, let us say for this layer, close to earth, the sunlight intensity is low, but number of molecules are very large. Means that even the number is high, but only suppose if I have 1 lakh molecule, but the number of photons are only 100. So because of this, we can have 100 ions. Means far from the earth only we have few ions, and close to the earth also we have few ions, but in between these two, at one particular, the intensity is sufficient and the number of molecules are also sufficient, where we'll get high density of ions. And because of the high density of ions, the sky waves are reflected by these ions and it reaches the receiver. Depending on the frequency of these sky waves, they are reflected from this layer of the ionosphere and reaches the receiver. Suppose if the sky wave energy is very high, they can able to penetrate. So these rays indicates that the sky waves are penetrated through ionosphere. But if the energy is less, they are reflected. So is this part, the sky waves which are reflected from the layers of ionosphere, it is just similar to total internal reflection taking place in optics, where the entire light is reflected back into the same medium. So here the sky waves, using these sky waves, we have radar communication, satellite communication, television communication, etc. So next one is space wave propagation. Space wave propagation. So in this space wave, the signals, the waves travel from the transmitter antenna to the receiver antenna in a straight path, in a straight line path. So here, observe here, the transmitter antenna and receiver antenna must be in the same line of sight. Both must be in the same line of sight because the space waves travel in a straight line. Because of that reason, the transmitter and receiver must be in the same line of sight. That is the condition for space wave propagation. So here we have two types of line of sight propagation. One is from one of the antenna on the earth to other antenna on the same earth. So this is earth communication. So line of propagation on the earth. Or we can also have line of propagation from antenna to the satellite and then satellite to the antenna. So this is called satellite communication. So first we will see earth communication. Means we have an antenna which is sending the space waves and it reaches to the other antenna on the earth surface. So here the frequency range of these space waves is more than 40 megahertz. So it has more frequency, means that the space waves penetrate through the ionosphere in a straight line path. So because of the line of sight, as we said, line of sight, there must be in the same line, transmitter and antenna must be in the same line for the propagation because of the straight line nature. So suppose if the antenna is situated in such a way that this the space waves may get blocked at the horizon, the earth horizon, the curve, because the earth has a curvature. So some of the space waves may get blocked on the horizon. So in order to avoid that, what we can do is we can increase the height of the receiver so that both the transmitter and the receiver, they are in the same line of sight. So this is so due to straight line space waves, the waves are blocked by the earth. So to avoid that, what we can do is we can change the height of the transmitter or height of the receiver, that we are going to see. So here we have some terminology. Radio horizon. Radio horizon means that the maximum distance up to which the transmitter antenna can send the signals, because of the line of sight propagation, these space waves may be blocked. So they may reach up to here. After that, these are getting blocked. So in order to avoid that, what we can do is we can change the height of the receiver antenna or height of the transmitter antenna. So DET is called the maximum distance up to which this transmitter will send the signals. Up to only this particle, because of the curvature, this space wave cannot reach to the other end, beyond the horizon, right? And maximum line of sight distance. So this is the distance between the transmitter and the receiver. So by adjusting their heights, what is the maximum distance for which the transmitter can send the signals? So DR is radio horizon of receiving antenna. It means the maximum distance up to which the receiver can receive the signals. And HT is the height of the antenna, transmitting antenna, and height of the receiving antenna, and R is nothing but the radius of the earth. Now we are going to see the expression for maximum line of sight distance, DM. So here this is the figure showing. So from this figure we can see that approximately this is HT, the height of the antenna. So from Pythagoras theorem we can say that R plus HT whole square. This is R plus HT whole square. So here this is hypotenuse. Side square is DT square plus R square is equal to R plus HT whole square. So by simplifying, so here the height of the antenna, which may be in 1 kilometer, 2 kilometer or something, but the radius of earth is very high, 6400 kilometer. So compare it to the height of the antenna, we can height of the antenna is very less than the radius of earth. So neglecting this ht square term, so dt is nothing but radio horizon of the transmitter. So dt is equals to square root of 2htr. Similarly, dr, radio origin of the receiver antenna, is this much. So what is the maximum line of sight distance? dm is equal to square root of 2htr plus square root of 2hrr. So this is the distance, maximum distance between the transmitter and receiver. So satellite communication. So here nothing but the antenna is there on the earth surface, and by following the line of sight propagation, we have a satellite. The space waves are propagated from this antenna directly to the satellite, and here the satellite will have both the transmitter as well as receiver. Nothing but we can say that it is a repeater. So it receives it, after that it processes the signal, and then again it transmits the space waves to the antenna which is located on the earth surface by following the line of sight. There must be antenna, satellite must be in the same line of sight of that of the transmitter, and similarly the satellite must be in the same line of sight of the receiver. So the applications of this satellite communication, nothing but the TV broadcasting, and we have different geostationary satellites dedicated for different purpose, to take the pictures, to take the Earth's environment, weather forecasting. For all parameters, we have dedicated geostationary satellites, right? So all three propagations, wave propagations, were explained in one figure. So observe here, we have ground wave, where the ground waves follow the curvature of the earth, and the sky wave propagation. So these sky waves are reflected from different layers of ionosphere and reaches the receiver. And the line of sight propagation, as we said, line of sight propagation on we have earth, on the earth, or satellite communication. So here a line of sight, here we have an antenna and aeroplane. So these always must be in the same line of sight for propagation of the waves. And this is the satellite communication. So from earth to the satellite we have uplink, we can call it as uplink, and from satellite to earth we call it as downlink. So this is about the radio waves propagation in space.